thanks for coming. I'm going to talk about different databases today. There have been some very weird overlaps with some other talks, like the last one from Alex and also the keynote from Venkat in the morning, because I want to start to talk about tribalism. And tribalism is that people form a kind of random groups and they say the other ones are stupid, basically. And you find that everywhere. It's a really human thing. Like, for example, these two brands, they can go at each other while everybody agrees both brands are pretty good. Both brands are also pretty similar. In our business, the same happens, right? That is all over the place. You have two things that are really trying to be as similar as possible in terms of how you use it, but yeah, still they hate each other. In editors, I think it's the worst, because it's so obvious that to edit a file, you can do it in any editor. Any editor gets the job done. Only the ones you're comfortable with is really nice, and switching to another editor is horrible, even though it's fine editor, but it's different. So people really use one editor and really get comfortable with it, and then they declare that the other ones are rubbish because they're not as nice. In the database business, it's also kind of similar, because if you use one of those, they are actually quite similar. But they are all kind of a little different. If you want to change the project from DB2 to SQL Server, it's pretty much always possible. It's also always horrible, because there will be all kind of little things that will just mess you up, but basically you don't really gain anything. They're really very lateral. So then you get the traditional tribal things that happen mostly when things are similar. When you can do, when it's really symmetrical, that you can do the same things with the same databases, and that and then you can compare. So, but about 10 years ago, a bit more, I think, NoSQL happened, right? So it became clear that you couldn't do everything you wanted with SQL databases. So all of a sudden, there were like millions of those. They're all over the place. And so that, but most engineers, and maybe still, were still in the mode of the old databases, and then you think, well, you think about it, you pick one, you get really good at that one, and then you use it for everything. And that's not going to end well for a NoSQL database, because largely they are specialized databases, like ElasticSearch, Redis, RocksDB. They have a really specific aim in what they want to be. So then, and that helps a little bit against tribalism, because then you get like this kind of comparisons. Which one is better? Well, obviously it depends on what you want to do. For one thing, one is better. For the other thing, the other is better. So then it makes a real comparison kind of pointless. So back to the specialized databases. So if you have more than one database and a specialized one, so that means that you use more than one at the same time, and they have to cooperate somehow. Well, how do you do that? Well, one way is the microservice you all know and love. Well, love a little bit, maybe. So I'm not going to bore you by explaining what a microservice is, but the gist of it is that you divide up your code, and in every sub-part service, you can choose whatever code base you want to use in theory. You can use your own data store, and you only communicate with the other parts using an API. Right? That's kind of what it comes down to. So in that case, if we have a few of them, it looks like this. We have microservice service, they all have APIs, and they all have their own data storage solution. So that's fine, and that usually kind of works. And then the answer to the question of how do those databases cooperate, well, they don't. They have their own world, they never meet each other, so we're in business. But we don't always get away with that. There are moments when you have like the same data but you really need it in different services, but from a kind of different perspective, in a different way. It's not, because if you think about it, if you have, it is not like personal address data is particularly well for MongoDB or something, or that metrics go in this database. It's usually about what you want to do with the data that defines what database will make sense. So it's inevitable that at some point you will have two places where you want the same data but in a different perspective. Let me explain. So, for example, we have an application in a really, really high level view of it. We have an application, it's in some language, it has a database. For example, SQL database doesn't really matter. It has some analytics code, and it has a general UI to do its thing, and it has an analytics UI. And after going to a conference, you think, well, we should do a microservice, right? Because that's what one does. So we are going to split it up. Yeah, and so there is a lot of there is something you could argue for this architecture. So, for example, you can develop and deploy analytics and applications separately. And you can use a specialized analytics database that's better suited for this kind of work. Maybe something for like Hadoop, or maybe even Elasticsearch, could be anything. And yeah, and the code base are separate, so you can use another technology if you want. That's all very nice, but if you look at it, what is that thing? An analytics API. Because if you think about it, if you want to do most analytics, you want to do the analytics over this data, right? This is the data you want to do analytics about. That's the database you want to do analytics with, but you need that data. It's not like that's a different microservice, so you can't access it. That's not going to work, right? So do you get something like this, right? You just connect to the other microservice and say, give me everything, you download the whole thing, and then you're going to do the analyzing. This is kind of what batch is. And if your data set is small, you don't need all the analytics all the time, well, you can get away with it. It's a bit of a weird way to put it, but it kind of works. So usually you can get this kind of constructions that you have a sort of REST model on top of it. So you can get all the IDs, you do some really basic queries, and then you can just download them individually. But still, you are downloading a lot of stuff over and over again, and you don't know if it's changed. So it is even more inefficient than this one. Then at least you got everything in one download. It's efficient in that sense. So you could do something like this. It's not really okay, of course, apart from all the security implications of something like this. But it's also not, in the microservice point of view, it's also not abstracting away the database, right? Because you can see it clear as day that which database is in there. So that also doesn't really work. So what you usually get is, traditionally, if you have two of these services, you have some kind of replication tool. Yeah, you have like the DB Visit, you have Oracle Golden Gate, you have a few. They cost a ton, every single one of them. But that does replicate all the data from one to the other. And then in this database, you can completely abuse it without interfering with this one. So you win something, but it does it does mean that we no longer can use the specialized database we want, because this kind of implies that they are the same or at least very similar. Yeah, you can't just plug in a random other database. And also, this is like a point-to-point connection. Maybe you can get away with doing it to another one, or maybe chain them, I don't know. But if you want a lot of these services, it's not going to end well. So it is for really like very small numbers. So a way around this is Event Driven Microservices. Anyone heard of that? A few, not many. Event-driven microservices are different from the regular microservices, is that they post things that happen, opposed to asking questions to each other, right? And that's kind of a mental shift because it's a sort of one-way street. And you have usually some kind of pub-sub bus behind it where you put on events, things that happened, and somebody might be listening and doing something with it, or not. You don't know, you don't care, right? So that would look something like this. We have our analytics service with the same code, and we try to capture the changes as they happen on the database, as they happen, all the records, when something changes, we put it in the event bus, and that's that from this point of view. The analytics service will simply listen to that event bus and build up their own analytics store based on all those changes. So if you have all the changes from the beginning of time until now, then you can rebuild all the data. Then you can rebuild it using any kind of database you really want, right? You have a lot of freedom then. Also, you have a really nice decoupling because this service doesn't know this service at all. And actually this service doesn't know this service, it just knows what to listen for. Yeah, so we make it a little bit more concrete for a client we did. We had one of those applications, and we use a change capturing, Debezium. I'm going to get into that in a bit. That captures all the change from the database. We put it in a Kafka queue. Who knows Kafka? Nice. And on the other side, we have another service that will materialize all those changes into a MongoDB database because we needed a lot of read scale. We were running that on like 10-node MongoDB, and this is a SQL database, so that wasn't going to work. So we needed to scale out, right? So that's step one. But getting back a little bit to the part before, change data capture. So that's when we ask a database to report all the changes. It's a really very straightforward notion. I can say it in 2 sentences, and I'm pretty sure all of you know what I'm talking about. But it is not straightforward. I really like this quote from Martin Kleppmann. Why can I not do MySQL pipe Elasticsearch? Because that's kind of what we were looking for, right? Like the Unix pipe, you take one database and you just pipe it real time into something else, and if it changes, it pushes the changes so they're in sync. That would be amazing. But that's not easy at all. And I'm not 100% sure why that is, but I think that over the history, all the databases have always tried to be the only database you will ever gonna need. And if you need something else, well, we'll add that feature somewhere. You want spatial, we do spatial. We do XML stores, we make XML stores. Every database has a lot of those features, and they try to do everything. They don't really want to compose with other databases, to cooperate. So I think it has something to do with that. But you can do it because there is something that pretty much every database has. And that's called a write-ahead log. And that's a notion that if you change the database, first of all, what you do is you put that data, that change on some kind of queue that's persistent, that if the database crashes, it's safe. And after that, you process that queue and you actually mutate the database. Every database calls it differently because I honestly believe they all invented it separately in their own way and came down to pretty much the same thing, but not completely. So archive log, op log, write-ahead log, or bin log, pretty much the same thing. So, and you can use that for several things. Like, for example, if your database crashes, you can use that to make sure you can get back to a consistent state. Because if you are mutating data on the fly and then you pull the plug on the machine, anything might have happened, right? There might be semi-written records, But if you make some snapshots and then you replay the write-ahead log of the last seconds of its life, then you get back to at least a consistent state. You can also use it to replicate data, right? So what pretty much all those databases can do is that you have identical ones and you scale them out horizontally and they all consume the same write-ahead log, so they all have the same changes, so they end up with the same data. So that kind of works, but it's not really an API. It's more like you just hack into something and you kind of figure out, oh, well, maybe I can do this. It kind of works. I have to shout out Postgres a little bit because they actually try. There is an official way to do it, and I like the way they put it on their website, that they use a coherent, easy-to-understand format, and that's only since last year. The database is 30 years old or something, but that tells you something about how it was before, because it was really, really hard to get that working right. It's easy to get working nearly right, but to get it right is really hard. So for that, there is a very nice project called Debezium. Anyone heard of it? Nobody. Okay, nice. It's from Redhat, and it aims to standardize this part of change data capture. Like, you point it to a database, and it does the real dirty stuff of figuring out all the different types and everything, and it posts it to Kafka. It uses the Kafka Connect API. It's pretty young, it's 0.9, based on a research project, but for now it supports 3 for real and 2 experimental. So Postgres, MySQL, MongoDB, and they're working on Oracle and SQL Server. And yeah, again, it seems like a really straightforward thing to do, but there are so many tiny differences in all kind of obscure data types that the different databases use that are nearly the same, but not quite. So there is a lot of fixing up for the really small things to make it work. Kafka is the broker we are using. So that's basically, you can see it as a message queue. It's not really that technically, but you can look at it like that. There's a Connect API, so that's an API you can use to as a source API or a sync API, and the source is like Debezium that injects it into Kafka, and there's also sync that streams the Kafka to the data to another database, for example, or something else, whatever. Streams API is also interesting. We'll get back to that too. That is an API that consumes Kafka topics, does operations on them, and then puts them back into Kafka. With that, you can kind of combine streams in different ways, and that's quite crucial. We'll get to that. So one of the features of Kafka is that, first of all, it's really high throughput. It's really, if you have a decent setup, you can do millions of messages per second. And it is persistent. It's basically tailing a file, which you write to as well, with all kinds of fancy things around, but that's basically what it is. What makes that very powerful is that, unlike the traditional message queues, it is okay if there are slow and fast consumers together. Because generally, if you have an event queue and you put in a lot of events, one is quick reading, another is slow, that means that it's all in its head, right? It can't discard anything until everybody has read it. Kafka has no problem with that because it writes everything to disk. So that's for this also really powerful. So getting back to this picture and making it a little more concrete is that we have a source database, we put it to Kafka, and then we materialize it somewhere else. But it is a little bit trickier than that, because if we have some kind of SQL database, in SQL, it's really nice to denormalize things. Put everything in separate tables, and you never repeat yourself, like dry everything. But that does not make sense for every database. Because if you have, for example, persons, and they have like communication things, and generally, you would, if you query them, you would join them together, and then you get like the data you want. But a database like MongoDB, it would make way more sense to just put it together and you query it as one thing. It also makes more sense because you can't do joins. So that's going to be painful if you want to do that. So in order to, so if you would do this in the naive way, you end up with a relational data model in MongoDB where you can't do joins. So that's not good for anybody. So you need to do stream processing. And again, it's one of the concepts that's pretty straightforward, but if you think about it, it's quite involved actually. So what happens? You have one table, so these are tables essentially, with all the changes of that table from all time, and this too. And then we do a transformation, and then we insert it in MongoDB. So, and these are generally, I mean, if it's like a stateless transformation, like put a name to uppercase or something, that's easy, because you don't need any data for that. But if you want to do a join from like this, if you think about it, because the order in which those changes arrive, it's undefined. They just show up when they show up, right? So you actually need to store all that data, right? So actually you have to store everything that comes from one side, everything to the other side, and when something, and then you basically build up your whole running join statement, right? Because otherwise you can't know if there's a change from this one. You need to know if there's one for the other one. It might have been a year ago. You don't know. It could be anywhere. So actually, that data store that helps you doing these kind of transformations, they can be massive. They can be much bigger than either database. So it takes some. It's a bit more serious than it looks at the first time. So let me do a little demo of it. I have been burned badly by using conference Wi-Fi, so I have a little bit of a data center down here. I don't know, I hope I don't trip over it. And let me see to mirror it. Of sorts. Well, fair enough. Okay, so I'm going to log into my dinky little data center here. Oh, shit. Okay, so I have a Docker compose file here, and it will start up some containers. I'm not going to really explain that, but I'll talk you through most of it. So it's going to spin up a few containers: a Mongo database, a Neo4j database, a Kafka cluster, so that's Kafka, Zookeeper, Kafka Manager, a few other things, and a Postgres database. That's it. So it's actually, yeah, it's quite involved. Like Kafka clusters aren't really for the faint of heart, but you can make it work. So now I have a Postgres database, but I have no data. So I need to make a data to import some data. So if I look at, I just create a database, something really basic, and I load in a file with some random data I found on the internet. All right, so now I want to take a look at what Kafka is doing right now. I hope it will be readable somehow. Let's see how bad it is. Something like that. I need to define the cluster. This is not particularly interesting, but we'll have to get through this quickly. This. and make it a little bit more responsive. Okay, nice. So now I have 5 topics. There's pretty much nothing happening because I didn't really start it all up. So the mockup test bear topic, it will contain most of the database. And to start it, I will need to tell Connect to start monitoring the database. Now they haven't really been introduced. So for that, that has a REST-based API. So I will post a JSON file to that endpoint. The JSON file looks like this. I'm saying like this kind of database, and there it is, and put it to that topic. So let's try that. Well, this says okay, so that's good. And now if I check here, it doesn't update too quickly. Look, and now you see there's a lot of activity going on. It's throwing in a lot of messages. So now we have kind of a completely linear view of that database, like all the changes that ever happened in their original order, so to speak. Right? But so yeah, it's done. So it says no more messages per second, so this is the total number. So in that sense, it is not a particularly useful way to look at it, but we'll get back to that later. So if I connect to my Postgres database, reconnect. Come on. Here we go. So it's actually a database of movie rentals, to be very, very not up to date. So there are, for example, there's a table with actors, fake actors, obviously. So, for example, if I would change one of these, like Nick Wahlberg is obviously called Bob Wahlberg, and I save it. Come on. Then so now it's 820, and if I reload, it's 821, because that change has been added to the end of the queue. So now what? From there, we need to do some streaming. And I'm going to show you some of the streaming. Let me set this up. Oh, wait. I think I did that wrong. One moment. This one. Anyway, so while this runs, I'm defining some sync here. So this is where I will write the MongoDB data. So some of them are direct, like this rental is the rental table, the inventory is the inventory table. If I compare this with the Kafka topics view, there are a lot of topics now. And there are like, like these are actually topics that model the tables themselves. Now, if all is well, I can check in MongoDB. Let's go to my little dinky cluster. There it is. And then we have this one. And we have like, I don't think I can scale this one. So for example, I have the actor collection. I don't know why it's so slow all of a sudden. Anyway, so you have the actor collection, so that's pretty much the exact same thing you had in SQL, but now in MongoDB. That's in itself not extremely useful, but like the film one, I did some operations there. I'll show them you in a bit. Here, I took all the actors and I grouped them together and put them as sub documents inside the movie, right? So if I have, yeah, it's going to be tricky for the people in the back, but I have a document here of a film that has actually a list of all the actors with all the data from the actor table. So all the data is replicated. So that means that if I want to make a web page that queries that film, you only need to do one ID-based query to get all that data you need, right? It's a lot more efficient than having to join everything on the fly. Also, if I would put this, for example, to Elasticsearch, for example, if I want to look for a film and I know one part of the title and I know one part of the name of one of the actors that plays in it, that's not a query that a relational database will like. Because even though it's possible, but you have to really make a lot of indexes, you have to really get it just right. But for a store like Elasticsearch, it's fine. You can just do a full text search. So then you can just join all the data you need in the way you want it, when you want to access it, and then you can search to it as much as you like. Another way to look at that data, let's see this one, is Neo4j. Who knows Neo4j? Nobody. It's a graph database, and it's a really interesting way of. It's quite similar to a relational database, and sometimes not similar at all. But for example, I can query a certain actor with last name Garland. So there are two of them. There is Humphrey, Al, and Kevin. And for example, now I just loaded the movies, the actors, and which actors played in which movie table into this one. So I can, for example, expand. If I would, for example, want to know is there a movie where more than one Garland played in, right? So if I expand this, you get a lot of balls. And then if you look here, there you see there's a special ball, because that's one that's pointed by both Garlands. And I can expand this one too, etc. This is not a very scalable way of working with data, but it is fun, especially to shake them a little bit. But you can do actual queries, like this one. Yeah, again, I can scale this one. So this is a Cypher query. It's a query language of Neo4j, and you have to see it like a ASCII art kind of thing, because you match an actor, some kind of actor with a certain last name, with some relational. That's an arrow, right? Arrow plays in some film called F, and then you have another arrow, but the other way, and you have another actor named Garland, right? So it is actually, this query is a graph in itself. Two things that point to that same movie. And this is all possible in SQL, but if these queries get a little bit more complicated, the SQL queries melt your brain. Even if they technically maybe work, but this is so much nicer way of thinking about data in certain cases. So if I run this one, then it just says these two films, right? Yeah, so that's the demo. I'll be quick. So, a few more things I want to address. One nice thing of this approach is that it's really friendly to legacy systems. Because if I have some service that does something and uses a SQL database, especially one that's supported by Debezium, I can just install the plugin into the database and I can go play, right? I don't have to touch any of this. And that's because, yeah, we can always think about we want to build the next cool thing, but as we are building lots of cool things, there's a lot of things that are not so cool anymore, but still works, still useful. So it is an important property. So, and even on production data, you can pretty easily do that. And then you have live data of the changes that are there. And it's not that intrusive to that database, right? So it's a fun way to advance your product. Security is an interesting way, interesting aspect of this, because on the one hand, it's generally a bad idea if you have sensitive data to go spread it around and put in all kinds of different databases all over the place. But at the same time, you can also, for example, if you need to open up your database to a third party using some API, if you do it in a traditional way, you have to really make sure that you exactly define which data they're allowed to see and which data they're not allowed to see. But what you could also do is just replicate exactly that data to a completely different system. And then they can abuse that system all they want. If they compromise it, if they DDoS it because their sites get scraped, doesn't really matter because it's different than from your own system, right? So it can also be a plus in terms of security, but it's definitely something to take into consideration. Also, there's some question about the legal part of GDPR, because there, in some cases, you have to prove that it's gone, and that's hard in a thing like Kafka, because it will, if you delete something, it will say, yeah, well, delete it eventually. It will get garbage collected, but it's basically impossible to know. And if that's good enough for legal minds, that I guess we're going to find out. Also, as I said, it's easy for integration because you can really think about the integration part, what it needs, how it needs it, and how it can use that in a more efficient way. So you can pick the database exactly for their use case, and your own database gets basically left alone. Also, you can play around a lot because everything here is, you can just throw it away and rebuild it because all the data is in Kafka, right? So if I do something stupid, I mess up this database, I throw it away, I rebuild it, I reload it from Kafka, this system will never notice. And that's in itself also powerful because then you can get a bit more brave with what technology choices you do. Another thing that I think nowadays pretty powerful is things like GraphQL. You can generate APIs on top of something like MongoDB quite easily. It's hard, though, to make it exactly do what you want. It's easy to do it nearly what you want. But as we can define what MongoDB looks like without touching the rest of the application, it will, yeah, you make a very good chance to really make a very easy, to advance really easily there. But it's not all easy. One of the big challenges of this is eventual consistency. When I change the source database, then it will change the destination database. How long will that take? No idea. Typically, it's quick, but yeah, it's hard to know how long that is, because maybe if you dump on 1 million changes at once, they will all end up being at the back of the queue, right? So you may have to go through that lag first. So maybe at some point there will be a bit of lag behind the changes. So you have to take that into consideration, that when you design this, that you don't really know if it's up to date yet. Also something to take into consideration is that this is not going to increase the write performance of your source database, right? You're still taking it through the same database. So if that's struggling with that, this is not going to make it better. It might make it better indirectly because you can take read load and indexes away from the database and put it somewhere else, because that can help if you remove indexes, because you don't query anymore. But if you want to really have a lot more performance there, it's going to be tricky. The infrastructure is pretty complex. If you do one Docker compose up and it works, then you're really happy, but it's pretty gnarly at times. And another thing I want to address is that the development cycle of the streaming code is kind of hard. Because if you have a certain way to transform the data and put it somewhere else, right? I change that code, I deploy that code. That does not change the data it already processed, right? So technically what I need to do is throw away all that data and rebuild it. For a dinky little database like this one, it's completely fine. But if you have like 500 million of rows, then it will take hours, maybe more. So it's not as easy to code as just changing something and press F5, right? You really need to think about the effects of your joins. Yeah. And finally, if you take this whole architecture with a source database and possibly multiple derived databases, you draw a box around it and give it a name. That's called a multi-model database. And I'm not sure if that's really going to fly, but I'm really interested in looking at it. For example, is Cosmos DB from Microsoft that has that idea that it kind of abstracts away all of this. But you store data and you can then choose how you want to see it in a persistent way. So that might be, that also might be interesting. But finally, what I want to talk about, really finally, I said finally a lot, is that this is like a really cliche. Like if all you have a hammer, yeah, nail. And usually people use it to indicate that you use the right tool for the right job. But the deeper meaning to me is that the tool in your hand influences how you think, right? Because if all you have is a SQL database, you think relational. You think how can I do that with a join? Yeah, it can be done. And generally it can be done. But it's the wrong question, can it be done with SQL? It's a bit more refined than that. So because if all you have is SQL, then you think if you can make it work that you don't need anything else. All those different databases, I don't need it. I can just join, and it's beautiful. And yeah, you kind of do, but you're missing out on the way they think, because like the document database, the graph databases, they have a really different way of thinking. And with this, you can really benefit from that with actual real data without having to build a new system. So I think it's, even if you just play with it, it will make you a better engineer. So that's all I have for today. Are there any questions? Yes. Well, yeah.
And it's relational.
Yeah, so if I have a relational database with no foreign keys.
Yeah, how do you generate, for example, a MongoDB entry, but containing all the information?
You can do that.
Association somehow, but how do you input them?
Well, yeah, there is a DSL from in Kafka Streams that does that defines how you do all those transformations after another.
Okay.
That does not cover every single data model. You can't really express everything in it. There's a even lower level API that we are using, where you really have to define, like you take this topic and you put everything in a local store, and you put that one, put everything in local. When it matches, you emit another one. So right now there isn't really a kid-friendly way of doing it, but it is very doable. But again, you lose the notion of foreign keys. They are not really foreign keys anymore. It's just things that happen to match. Yeah. And if you get your streaming definition wrong, then it will not complain. It will simply not match. Yeah. Or worse still, it will match to something completely unrelated. So it is a bit of a rough area there.
what if we take it a step forward and, for example, we have a relational database, but we want different outputs. Same structure, no foreign keys, just tables, but we want, for example, in MongoDB to have a specific JSON input.
Yeah, that can be done. I mean, especially if it's like a transformation that you can do on each message, that's easy because you can just, you can just do them one by one. The more expensive ones are when you joining large data sets where you need both of them to be complete. But yeah, that's no problem at all.
Okay, thank you.
Anything else? All right. Thank you very much. Oh, wait.
Did you compare it with inserting it into multiple tables?
Okay.
So as a comparison, did you compare it, for example, if you start from scratch, a new project, let's say, you don't have legacy data, comparing it to inserting into the same data when you get it into multiple databases compared to replicating?
Yeah, I mean, you can do that, but it will complicate things in another way, because then what if one of those are down? Then it's not in the other database. How do you get it later? So it's the same thing. You need to be able to take that data and from there populate the database. If you have to insert in every single one, then first of all, the insert gets heavy. And maybe there is like, at some moment it's really busy and then it might fall over. And also, yeah, if you drop requests for whatever reason, there's no real way to get them back.
Thank you.
Anything else? Well, time for coffee, I guess. Thank you.